Okay, this is part 3 of this screencast covering the history of collisions and their importance in particle physics in the 20th and now into the 21st century. The first major discovery that was made at the LHC occurred in 2012 with the discovery of what is called the Higgs boson. The Higgs boson was a mathematical piece of the standard model of particle physics that was predicted back in the 1960s, but no experiments done during the latter half of the 20th century detected its presence. The LHC in particular was built primarily to discover the Higgs boson. Now, exactly what is the Higgs boson? Well, the Higgs boson is the piece of the theory, a particle that exists within the theory that gives all of the other particles the property of mass. Now, mass, of course, is considered to be fundamental, and recall what is meant by inertial mass. The greater the mass of an object, the harder it is to change its velocity, the harder it is to accelerate. Where, however, does that property of matter come from? Well, it comes from this particle that exists within the standard model called the Higgs boson. Now, here's how you can start to wrap your head around exactly what is meant by the Higgs boson. This is a common analogy that is used by physicists. Picture, for example, what is called the Higgs field. And a nice analogy to use is to picture the Higgs field as a room, as a party, and there are party goers, for example, that are present. And then let's say that somebody else comes to the party. Let's say that a guest arrives at the door. Let's say, however, that that guest is not very popular. So then therefore, as that person moves through the room, as that person moves through the Higgs field, the other party goers don't necessarily come up to that person to say hello. In other words, the person doesn't interact all that much with the Higgs field. This then means that that person has a low amount of mass. Now, it's important to realize that the person did not already have this property of mass prior to arriving at the party. How that person interacts with the party, that then determines the person's mass. So now picture, for example, somebody else that comes to the door, and let's say that that person is very popular. So then all the other party goers then go to the door and they interact with that person to say hello. So the interaction between that person and the Higgs field, the party itself, is very large. Therefore, that person has a large amount of mass. Once again, it's important to realize that the person doesn't already have this property prior to arriving. It's how that person interacts with the property, or interacts rather with the party, that then determines the person's mass. So basically what was done in this experiment in 2012 is that matter was slammed together so hard that it broke off a piece of the party. It broke off a piece of the Higgs field, and that is what is meant by the Higgs boson. Now, since the discovery of the Higgs boson, the LHC has been operating at its highest possible energies. Recent experimental results indicate that the LHC may have seen new physics beyond the standard model, but such discoveries have not yet been confirmed. The LHC is designed to operate for decades. So what may happen in the years going forward as hopefully new discoveries are made at the LHC? Well, it's been hypothesized that we might be able to cram matter together so tightly in the highest energy collision experiments possible at the LHC that matter may actually undergo final gravitational collapse to become a singularity, that is, to become a black hole. That black hole would be, however, much smaller than a proton. Now, should you be concerned about the possible creation of black holes within the LHC? No. And the reason for that is as follows. The famous British physicist Stephen Hawking, back in the 1970s, discovered that black holes are actually not quite so black. For pretty complicated reasons, they actually give off a little bit of radiation called Hawking radiation, and their mass decreases as a result. So, for example, if we do create microscopically small black holes within the LHC, once again much smaller than a proton, they would almost instantly evaporate, giving off this radiation. This then leads to a decrease in mass, and eventually those black holes would no longer exist. That radiation, by the way, is called Hawking radiation. Hawking radiation has never been observed in nature. However, if we do observe Hawking radiation inside of the LHC, this then means that we have, in fact, created black holes within the LHC, and we can therefore study their properties. Okay, and then beyond that, what may happen? Well, as I said, physics today is basically two things, general relativity and the standard model of particle physics. However, neither theory all by itself is a complete theory of nature. In other words, you can't use the mathematics of general relativity to describe particle interactions. You can't use the mathematics of the Standard Model to describe general relativity. In other words, the two theories are incompatible mathematically. They perfectly describe their relative realms of nature. In other words, general relativity describes perfectly the universe at the largest of scales. The Standard Model describes the universe at the smallest of scales, but they don't fit together mathematically. This then means that there has to be something else underneath. In other words, a final theory of nature, a final theory of physics that combines general relativity and the Standard Model into one mathematical framework. As of now, we don't know what that theory is. We have some ideas. One of those ideas is referred to, for example, as string theory. This slide here is depicting some of the mathematical details of string theory. But as of now, there is actually no experimental evidence that string theory is in fact correct. String theory also has some competitors. This is part of the purpose of the LHC. Part of the purpose of the LHC is to discover new physics beyond the Standard Model, perhaps point the way to a final theory of nature. And then if we do ultimately discover that final theory of nature, then we may be able to apply it. We might be able to, in some manner, master time and space, energy and matter. And then what will be the technological revolution that follows from all of that? Hopefully this will all play out as the 21st century continues. Okay, that concludes this screencast here, covering the importance of collisions in particle physics throughout the 20th and now into the 21st century.